Okay. So let's get started. So today I want to continue talking about Datapath and controller. I start talking about the implementation of the ISA, right? And yeah, question. Yeah, it is on. Should be on. Yeah. Yeah, it is on. So the last time we talked about the microarchitecture, which we basically defined it as the hardware implementation of our ISA. We said that generally the format that we are following is what is called a data path and a controller for implementing our microarchitecture. This is again back to our what we call store program model and the von Neumann machine. The data path is basically a combination of all these functional units in our system, and the controller is one unit that basically takes the instruction as the input and make all these decisions about what should be done. For example, we said that there are some instructions that use 2 registers as their input. There are some other instructions that use register and immediate. So there needs to be some form of controller to kind of distinguish between these two and kind of orchestrate how the data flow in our data paths should look like, right? So that's the job of the controller. In this lecture, we want to go a little bit deeper into that. We talked about how we conceptually implement the controller. We talked about a finite state machine, and generally there are different states for it. We're not going to implement the exact finite state machine, but we're going to talk about those control signals, the outcome of your controller. But in your project, you're going to actually implement the whole data path and controller all together. So you're going to get a little bit more understanding of all these things. To make things a little bit simpler, we kind of just choose a subset of instructions that we discussed in the previous lectures. So we don't implement all of them. We only pick 10 instructions that you can see the list here. The reason that we picked these 10 was we wanted to have a representative of all these different types of instructions. But for example, in your project, you will see that we might change a little bit of this set of instructions and use other set of instructions. And then you will also, in your homework, for example, you will see that we, for example, ask you what would happen in our data path or in our controller if we decide to add this instruction or that instruction. In reality, so of course, given that we said that you're having this contract between the software and the hardware has to make sure that whenever it says, for example, I'm supporting RV32A, it supports all the instructions within this data set, this instruction set, right? So here we just make a subset of that to give you a big picture of how these things are done. But in reality, in real hardware, everything needs to be supported, okay? And again, as I said, the controller usually sits after our instruction memory. Sits here and takes the input. So there's a logic involving the controller, which we said this is basically our finite state machine. And then we're going to have a bunch of control signals, which we're going to go through one by one in today's lecture. And this basically propagates into the rest of our data paths in multiple different stages. And in order to distinguish between the data path and the controller, we said that we're going to show things that is relevant to the controller in blue. So whenever, from rest of this lecture, whenever you see things that are in blue, it means that they're coming from the controller. Okay? Any questions so far from previous lecture? All right. So now let's actually, very quickly revisit the things that we have done so far for our data path, and then move on to the rest of the data paths to have a complete figure. So we start with this. We said that basically the very first thing that we need to do is have a register that keeps track of our program counter. So this is the register that we are talking about, right? And this register needs to be connected to our instruction memory. The instruction memory has an input port which reads the address. We extensively talked about how long this address should be and so on. We talked about the L. And we said, for example, if you have a 1 kilobyte of instruction memory, you need 10 bits to address this. If you have more, you need more, and so on and so forth. But the output of the instruction memory is always 32 bits because in this specific implementation, in this specific microarchitecture, we're talking about 32 bits RISC-V, okay? So if in future we talk about things like 16-bit version or 64-bit version, then this becomes 16 or 64, right? But for now, we are focusing on the 32 version, all right? So the outcome of this is 32 version. To repeat the things that we have said so far, inside the memory, we are storing things in 1 byte blocks. So that's why we need to read 4 of them together in order to create that 32-bit, okay? So that's why when the next time we want to read from PC, we do PC plus 4, but nothing prevents you to read from PC plus 1 or PC plus 2. It's just something that you need to follow in order to make sure that you're reading the correct instruction, okay? The assumption of the compiler is that you are reading 4 by 4. So if you don't do that, you just mess up the instruction, okay? So that's why we are doing PC plus 4, okay? So at this point, we have the 32-bit version of our instruction. We usually show it this way. Think about it as an array that has 32 bits, and we can access individual bits of this instruction, or this instruction array, okay? Any question from this part? All right. Then we said that, okay, we are now gradually adding more things to our system. The first thing that we added was the PC plus 4. For now, we assume that, the default is we always go to PC plus 4. So the way that we do it is that this, if we call this current PC, or I just show it as CURR underscore PC, what we need to do is that we need to create PC plus 4 for our next instruction, right? So this goes into this adder. So this is a small, tiny adder that we add into our data path. If you are not familiar with how we implement adder, you can take a look at your digital logic design. It's not important for us in this course that how the adders are implemented, but they actually have a set of transistors and they have a specific design to design the adder, right? So we have a small adder here that takes the PC plus 4, and here we have the PC plus 4 value. And then this one goes back into our register, and basically this is the input of our register. If you remember when we talked about register, we said register has this thing clock, and it has this thing D, and then it has this output Q. So in this case, we usually call this next PC. So this D is basically our next PC. The clock is clock. Whoops. The clock is clock. And our Q is basically our current PC. Okay? And as you remember, we said that the register is this thing that whenever the positive edge of the clock comes, the D would be getting the value, the Q will be getting the value of D, right? So whenever I change this doesn't get automatically updated. It only waits until the positive edge of the clock comes in, and then the value will be the next value. So we are assuming that in every clock period, we're gonna run one instruction. So this is like the life cycle of one instruction, and this would be the next instruction and next instruction and so on. Okay, so this is the way that we assume this is happening, and that's why we have this PC plus 4 and we have this registers. Okay. So moving on. Now we said that we basically adding more things to our instruction. Remember, the first part goes into our controller. I'm going to switch to red from now on. So this 7 bits, the first 7 bits goes into our controller. If you ask why the first 7 bit, if you remembered our table, the first 7 bits was our opcode, right? So all the controller needs to know is what is the opcode in order to make that decision about what needs to be done, right? So the first 7 bits goes to the controller, and the rest is added to our register file and to our immediate generator. if you again go back to that table that we had, remember, for example, the bit 15 to 19 was RS1, 20 to 24 were RS2, 7 to 11 was RD, right? So the reason that we are picking this is just, if you go back to that table that we had, these were the locations for all these things. So we just wire them, as I told you last time, the correctly wire them into the place that they should be wired, okay? So think about this as 32 wires, right? This basically. And what we do is saying that, okay, this is the 0, this is the 1, this is the 2 all the way. So I'm going to pick, for example, the 7 1 all the way to 11 1, and I'm going to wire them all together into, for example, my RD, right? So this is just a basic wiring. In your C program, this would be basically, think about this again as an array with 32 bits. You just pick the right indexes to connect it to your RS1, RS2, and RD, right? And then for the immediate generator, you just pass the entire immediate generator to our immediate generator, because if you remember, the immediate was kind of like scattered around everywhere. And this immediate generator, you're going to check the opcode and understand which type of instruction is this, where the immediates are kind of stored. And at the end of the day, it's going to give us the immediate that we want. And this one is sign extended and 32-bit, okay? So the immediate generator inside, first understand what type of instruction is this. This is an R type, this is an I type, S type, B type, U type, whatever. And then based off that, has that table in mind, and then kind of like, again, wire it together and sign extend it appropriately, okay? And the outcome of this immediate generator would be the 32-bit version, sign extended, perfectly, work well, okay? And at this point, we also have, so these are the outcome of our register file. This would be our RS1, and this would be our RS2. This is the value of RS1, right? So kind of like I'm showing it this way to kind of distinguish between the name of the RS1 versus the value of RS1. So this is an actually 32-bit version, the 32-bit value, okay? And from now you can ignore what is this write data, because it's coming from later stages of our data path. So we're going to talk about this specific line that's kind of right now is kind of hanging in the air. We're going to talk about this, and we're going to go back and talk about this, okay? And then there are a bunch of signals that's coming out of the controller, which I'm going to talk about one by one once we move to the next stage of our data path.
So how come the func3 bits are not going into the controller?
So the question is, how come the func3 and func7 is not going to the controller? So the last time I told you that our FSM is actually first looking at the opcode first and then go to the func3 and func7. In reality, for performance purposes, we actually do another trick that I'm going to describe here. So think about this as the controller only knows that whether this is an R type or I type or U type or S type or B type. There is another trick that we're going to use, which very shortly I'm going to describe, in order to distinguish between the R type instructions and so on. The reason for that is we want to make sure that the controller doing the exact same thing for all type of instructions. Because if we move from R type then to the func3, it's kind of 2 steps, versus, for example, for load board, it's only 1 step. And that's not something we want to do. So there is another trick in order to distinguish between the R types and using func3 in some clever way that I'm going to describe later, okay? Any other questions?
How do we initialize the PC just from the calculator?
So the question is, how do we initialize the PC? Think about this initialized PC as a separate input coming from the operating system, from somewhere else that actually initialize it. To make things simple, we don't show that signal, but in reality, the PC actually has an external input as well that coming from the rest of the hardware, which is basically controlled by the operating system.
Is it like a multiplexer?
So the question is there a multiplexer here? Yes. Or sometimes they have 2 write inputs, and then there's a write enabled, for example, as well. So a register could have multiple write ports. We won't, maybe at some point I'll talk about that, but for now we are assuming that the PC is already initialized with the beginning of our program, okay? But that's a good question and a good observation. Other questions? Okay. So far so good. This is basically the part that we got into in the last lecture. So now let's talk about the kind of like the right half of our design, which is getting a little bit more complicated. All right. So I'm not showing the left half anymore. So assume that this part you have the 32-bit version. I'm also not, for now, not showing the PC+4 part, but just imagine that basically these two parts gonna, combine together. At some point, we're gonna just show you the whole picture. But for now, assume that this is your 32 version, and this is basically that 5-bit, 5 bits that goes into our register file, like this, okay? So now let's talk about this side of the things. Remember, we said that this point is RS1, this point is RS2, and this point is our immediate, the 32-bit version of our immediate. Okay? Can you see it, by the way, in the back? Is it good? Right? Can you see it well? Okay. So now we are getting into this point here. So this is, as I told you before, this is our ALU. The ALU is our arithmetic operation unit, which basically what it does is it takes this control signal called ALU operation, and based off these two inputs for the ALU, which I'm going to get to very shortly, it's going to do some arithmetic operation for us. If you go back to our table list of instructions that we had things like XOR, AND, sub, add, and all those things, okay? So all these operations actually happening inside this ALU. And in order to understand what the ALU needs to do, it looks at this ALU operation, and as you can see, this is a blue signal which is coming from the controller, and the controller will tell the ALU what to do, whether it has to be add or sub, and so on. And again, for now, assume that the controller knows the different types of R types and I types and so on. Well, I'm going to get to how we actually distinguish between those different operations. Okay? And the reason that it's 4 bits is because 2 to the power of 4 or 16 different operations is enough for our 32 version of RISC-V. Okay? There is only at most 16 operations. If you go and check it manually in the list of instructions, you will see that 16 operation is more than enough, actually. If we needed more, then we have to basically change this to 5-bit or 6-bit and so on. Okay? So, and then for now, ignore this 0 bit. The outcome of this ALU is this thing called ALU results, which is also 32-bit value. Okay? So we are adding, for example, 2 inputs, and we create a result which is a 32-bit output. Okay? So now let's actually look at these other things here. The first thing is this ALU source, and the reason that we have this mux here. So first of all, this is a multiplexer. All it does is that based off this selector, this signal here, which is 1 bit because it only has 2 inputs, so 1-bit selector is enough. Based off this selector, it either choose this one or this one. So if the selector is equal to 0, it will just connect these two lines together. If the selector is equal to 1, then basically connects these two together, right? So this is a simple multiplexer. And if you go back into our design, you will see that basically our instructions, the ALU operations or R-type instructions, were basically 2 groups of instructions. We either had always RS1 plus some doing some operation with some immediate, or we had RS1 some operation with RS2. Okay? And if you look back here, I told you that this is our RS1 and this is our RS2 and this is our immediate. So basically this line here tells whether we are picking immediate or whether we are picking RS2. And how do we know that? We know that by just looking at the opcode and using the controller. So basically the controller, depending on the instruction, by this trick here, tells whether we need to, our inputs to our ALU is whether RS1 and RS2, or whether it's an RS1 and immediate. And we don't have a scenario at which there is RS2 plus immediate. If we had that option, then we needed to change this data path some way. So when I'm talking about, for example, sometime in future, if I ask you what would happen if we have this weird instruction that does this, then it means that we maybe need to maybe add another multiplexer here or things like that, okay? So whenever we need to kind of like, move things around and have multiple different options, our solution is adding a mux somewhere in our data path. And in order to select which one to choose, we usually use the controller to generate that signal for us, okay? So ALU source is one of those control signals. It's the first control signals that we're going to use in our controller. Is that clear? Any question here? Okay. So up to this point, we are good, right? So let's continue. I already talked about this ALU operation. Again, it's a 4-bit number that is coming from our controller. So again, here is good, here is good. Now we understand these two parts. We understand this part and this part. And now we also understand this part, right? So we do some operations, and then we have the results. And as I said, for now, just ignore this. I'm going to get back to this to 0 and tell you why we need another output for our ALU, okay? So this point is a 32-bit number, okay? So now let's move on and talk about this memory part. So what is happening here is the results of the ALU could be the inputs to our memory. So this is our data memory. So this is where we actually access things, reads and write things from our memory. And as I said before, the data memory and instruction memory, which stays here, they're technically the same thing. But in order to show it easier in our data path, we're assuming that there are two separate physical entities, but they're actually the same. So the inputs, similar to our instruction memory, the memory has this input address, which is, again, could be 32 bits or could be smaller depending on how many lines we have. And then it has this output, which basically the results of what we have read from our main memory. Okay? So this is, again, 32-bit version. This is always 32-bit version. An additional thing that we have for our memory is write data. So remember, for our instruction, we don't need to write things to our instruction, but for reading things from our for writing things to our data memory, we need to provide that write data, okay? So this is additional port that we have. And the reason that why we are adding our ALU to our address and why, for example, we're not using our RS1 or RS2 is that, again, if you remember from our load word was always address like this, right? So we always said that we're going to have register relative or relative address, so base plus offset, which our base was always RS1 and our offset was always immediate, okay? So if you go back to all the types of load that we had, all of them was like this, okay? So it means that this is basically, this is our RS1, this is our immediate. The operation that needs to be done would be add, and based off that, this results would be equal to RS1 plus immediate, right? So that's why the address is actually needs to be connected to our ALU, right? The alternative would have been that we had like a small adder here, and then we kind of like, add these two things here and then connect it to here. But since we already have our ALU here, there's no reason to have another adder to make our data path bigger, right? So we kind of reuse our ALU in order to generate the address, okay? So I'm going to just delete this part to not make you confused. So that's why we have connected the output of the ALU to the address, okay? And again, if you look at the store word, the same story. The RS1 plus immediate was the address for store word. So regardless of whether we are doing store or whether we are doing the load, the address for that activity in memory was always RS1 plus the immediate. Does that make sense? Any questions?
So if the ALU is occupied in computing the address where you're going to load or store the word from, where do you store the actual data? Where does that go when you're...
So the question is that if the ALU is occupied with computing the address for load and store, where do you bring the actual data? And again, if you go back, so first of all, for load, you're not providing data, you're reading from the memory, right? So for load, all you need to do is providing the address. and this is the way that we are providing the address. The data is actually coming from here, right? So for load, we are good. We need to just provide the address, wait for some time. The data will come in at this point. So this is the outcome of the load, right? Does that make sense so far? So the second question is, okay, what do we do with the store word? Because for the store word, we not only need to provide the address, but also we need to provide data, right? And if you look at the store word, if you remember store word was like something like this: RS2, RS1, and some immediate, right? And we told you at that time that RS2 is actually the data that needs to be written to our memory, to our store word. And if you can actually follow this, you will see that it's actually exactly what we are doing here. So we are providing this data, we are providing this additional wire here, which basically this is our RS2. So the RS2, the value of that register is the value that we want to write into our memory. Okay? So we are providing the address this way from this path, and we're providing the data from this path. And this is the way that we're providing data to our store word. Does that make sense? Any other questions? So another interesting thing from our main memory is that there is this two blue control signal here as well, which is called memread and memwrite. The reason for this is that sometimes we want to read something from the memory if it's a load word instruction, but if it's like an R-type instruction or I-type instruction, we don't need to read anything from the memory, right? So in order to tell the memory that, oh, we need your data if you put this address, because remember, this address will be always there. So for any activity, regardless, there will be a value here, but not all the instructions are load word or store word. So in order to tell the memory that this is indeed a load word and we need your data, we actually issue this signal and tell the memory that this is a memread, this is a load word, go and give us this data. So this line here, most of the time is just an invalid. So you can think about it as garbage. It's just random values in this line. Unless we tell the memory that this is a memread. And if it's a memread, when you put this address and we issue the signal to 1, then after some time, this becomes an actual value that is coming from the load word. Okay? So this is basically a control signal that whenever the controller sees that this is a load word, it's going to issue this equal to 1. Okay? And the same story for memwrite. So this one is for store word. So you basically tell the memory that, oh, this data that I'm putting here and this address that I'm putting here, go and actually write it to our memory. Otherwise, if we didn't have this, then even for R-type instruction, we just randomly writing things to our memory, which could generating mess up our memory. So this basically says that, oh, this is indeed a store word, this is a valid data that I'm putting in this line, and this is a valid address, so go and write this into this line that I'm telling you. Okay? You had a question here?
So
yeah.
This is all used for, is this only for the scope of hardware stored, or is this like same hardware used elsewhere for this one device?
So the question is, is this hardware only used for store word and load word, or is it used for other things? Which part of the hardware?
Huh?
Which part of the hardware are you asking?
Like this whole thing was
Here? So yeah, this is our data memory, right? So if we want to interact with our memory, we need to issue the signals. In reality, I mean, in normal operation, right? There are many instructions that doesn't have any interaction with our memory, like R-type instruction or R-type instruction. And in that case, both of these signals are equal to 0. So basically, this operation here has nothing to do with the rest of the data path. I mean, the signals are still connected, but doesn't do anything. So we can just ignore it.
And then if you're using this, like maybe something like an add median or something, with those AOE results, like.
Yeah, so the question is that if you have something like add-I or add, what would happen? And what would happen is that the other multiplexer here, which I'm kind of like, also showing here. And if you follow this, you will see that basically here we are bypassing the memory and we're putting the results here. and then we're putting the results here. So if this is an R-type instruction or I-type instruction or even like a branch instruction, we don't need the memory at all. So basically, this multiplexer tells that if mem to reg is equal to 1, pick the results from the memory. But if the mem to reg control signal is equal to 0, then just connect this to this. So we're kind of like bypassing our memory. Okay? Any other questions?
So this is the
Mem to reg.
basically just the same, like an order which includes our memory and.
So the question is that if mem to reg is an OR gate of mem-right, yeah, that could be one implementation of it. These are all implemented within our controller. And usually what we do is that we have a big switch case of all these and then just assign values to it. Okay?
What happens to the right box when you're storing a word? Like you need to read data, but you also want to see what happens.
So the question is, what happens when you want to store something to so if you want to store something to your memory, then everything can be ignored. So this value doesn't matter whether it's equal to 0 or 1. Because if you actually now look back, if I go to the next slide, you will see that the outcome of this is actually go all the way to our write data of our register file. So remember I told you that write data for a register file, I'm going to get back to it. That's where it comes from. And if you remember, for example, for R-type instruction, we had things like add, RD, RS1, and RS2, right? And so basically, this is our RS1, this is our RS2, and then the ALU source in this case would be this. Then we do, for example, ALU operation of add. We get our ALU results here. Then this will go here. This is not a memory operation, so we're going to basically say this should be connected to here. And this is actually our RD, right? And this is exactly what we want to have here. So we connect it to the input of our register file. And another thing that we're going to do is that we have this additional control signal that's called reg write, which basically what it does is tell the register file that this data here is valid, this address here is valid, so please write this data to your register file to this RD address that I'm providing. Okay? So this is the way that we're going to do that. And for store word, what happens is we provide RS2 here. We provide RS1 plus immediate here. We will tell the memory to write, so we will issue this to 1 as well. And we're kind of done. We don't need to do anything else. So it doesn't matter what we do here. We can do 0 or 1. But whatever we do, this signal goes here. But as long as this is equal to 0, nothing happens, right? So we tell the register file that, yeah, there is something here, but don't bother. It's not relevant to you. So you can just ignore it. Any other questions? So that's it for storing data. And that's kind of like, completes our data path for R-type instruction, I-type instruction, and memory instructions, okay? And the only thing that is remaining is our branch, because remember, I told you that the design that we have so far is only providing PC+4. We don't have anything for jumps, and we don't have anything for branches. So let's add that to our data path, and once we add that, we have everything that we want, okay? So for branch, there are multiple things that we need to do. Remember, our branch was always PC relative, right? It was PC plus some immediate. And for now, we are not doing JAL and JAL-R, which was RS1 plus the immediate, okay? So in our implementation, we are not talking about these instructions for now, okay? So we are only talking about branch equal, which the addressing for branch equal was PC plus immediate. Okay? So where is our immediate? This is our immediate, right? And then why are we shifting it to the left? Anybody? Yeah, so the first bit was 0, right? So we are shifting to the left so that we make sure that that first bit is equal to 0. So this is basically like the shift left version of that. And this is our new immediate. And this is coming from our PC. So this is PC plus immediate. And again, instead of using this, we are using this. The reason for we are adding another adder here is that we need this for our comparison. Remember, the branch has two things that needs to be done in the branch. We need to compare two registers, and based off that, we need to update our branch. So we cannot use the ALU for both things. That's why we need to add another adder to our data path. So this is basically gives us PC plus immediate, okay? And this is 0. Remember I told you about this 0. So this is not an ALU result. This is actually a 0, which basically, depending on what we want to do, for example, in the branch equal case, we want to do RS1 minus RS2, basically. And if this is equal to 0, it means that they are indeed equal, right? So if this 0 bit is equal to 1, then it means that these two are equal, so we have to actually take the branch, right? So we added this additional line here. And when we are adding these two together, we have the PC plus immediate here. We have whether or not this branch has to be taken or not taken here. And this is all we need for a branch instruction. So all remains is we need to kind of like, wire this back into the rest of our system. So if we put these together, you will get something like this. So I'm just showing everything all together for you. But for now, let's focus on this side here. So this is our immediate. This is left shifted because we're ignoring the zeros bit. This, if you look at, if this is actually coming from here, so this is our PC, and this is our PC plus 4, and here is our PC plus immediate, right? And this one, the PC source, is actually the control signals in order to decide whether we are picking PC plus 4 or whether we are picking PC plus immediate. And this line here goes back into our PC. So what happens is that instead of always connecting PC plus 4 to our PC register, we are adding a mux in here, which kind of decide between PC plus 4 and PC plus immediate. And in order to decide whether this branch is taken or not, we are using this PC source control signal, which this PC source control signal is nothing else but this signal coming from 0 ANDed with whether this is indeed a branch signal. Okay? So basically what the controller does is that first of all it checks whether this is a branch instruction or not. If it's not a branch instruction, then we don't need to update our PC. PC should be always PC plus 4. So that's why this line is coming. In addition to that, for branch instruction, it has to be branch, and it has to be branch equal. It has to be, equal, right? Because we are only implementing branch equal. So in order to know that whether RS1 is indeed equal to RS2, we are using this 0 signal, and we are ANDing these two together. So if both of them are equal to 1, this signal is equal to 1, which means that we are picking this part. And this part was PC plus immediate. If neither of these two, or at least one of these two, are not equal to 1, then we're going to pick this one, and this one is PC plus 4. Does that make sense? So for branch, it's a little bit busy. The first thing that we need to first know about whether this is a branch or not, that's the responsibility of our controller. It checks the opcode and see whether this is a branch. If it is a branch, we're going to issue 1 to here. So that's first thing. The second thing is that we need to check RS1 with RS2 here. And inside the ALU, we're going to just subtract these two from each other. And if the result is equal to 0, this signals become 1. So these two goes together and going to be ANDed together. If both of them are 1, the results of the AND would be 1. So this line would be 1. This is the selector of this multiplexer here. And the input of this multiplexer are PC plus 4 and PC plus immediate. So we basically are picking between these two. If both of them are 1, we're going to pick this. If neither of them are not 1, we're going to pick this, right? And this is going to go back to our PC. All right? That's how we handle our branch equal. If we have other branches, then we had to extend this and make it more complex, which we may or may not talk about in future. But for now, just imagine that this is the way that we're going to implement branch equal. Maybe that would be a good question in your homework, that how we do, for example, do branch greater than or branch less than or something like that. But all of them, again, follow the same principle. We need to check whether this is indeed a branch. We need to check whether that condition that we are checking, whether it's equal or greater than or less than or whatever it is, it's true. If both of them are true, it's time for us to take the PC plus immediate and not PC plus 4. Any question here?
Can we use more flags with the ALU to like less than greater?
Say louder.
Can we use more flags with the ALU to do greater than or less than?
So yeah, so the question is that, for example, for greater and less than, should we use more flags? Two things that you can do. Either use another flag here and maybe OR them together or something like that, or add them together. Or within your ALU, use the different operation. Maybe add a comparator that actually the 0 bits, your 0 flag could be changing depending on what operation you want to do. So for example, for equal, I just do subtract. But maybe for greater than, what you want to do is a comparison. They're actually a logic equivalent of comparison that you can add to your ALU. Okay? So either add another flag or change your logic inside your ALU. Any other questions? Okay. So this is kind of like the entire image of things that we do. So the last thing that I need to describe to you is this ALU control here, because still remember that we still don't know how to distinguish between our R-type instructions, right? So this is the trick that we're going to use that I'm going to describe in the next slide. But for now on, have a big picture of all the things that we discussed so far, okay? So again, we start from PC, we go to our memory, we have our 32 instruction here, we just wire them correctly based off the location of things. We send the opcode to the controller, we send all 32 bits to our immediate generator, and at this point we have our immediate, we have our RS1 here, we have our RS2 here. This mux was ALU source mux here. That this one basically decides whether we have to pick RS2 or immediate. It goes inside our ALU. The ALU using this control signal that is coming from the controller with some trick that I'm going to describe later, which basically decide that whether we have to do add or subtract or AND or XOR and so on. The results of the ALU is coming here, which happens to be the actual address that we need for our memory, because our memory needs RS1 plus immediate, right? And the data for our memory is also coming from RS2. And the control signal, the memwrite and memread, is also coming from our controller, which basically tell the memory whether we need to read or write. And the results of the memory is coming here. And the results of the ALU is also coming here. And here we need to decide whether we want to ignore the results of the memory or whether we want to actually load the data from the memory. If we decide to ignore, we're going to connect these two. This one is actually our RD. But in order to tell the register file that this indeed is RD and we need to write, we also use this reg-write control signal to our register file. And then the whole story about the branches was we added this flag. This flag goes into this AND gate. There is a control signal for the branch also goes to this AND gate. And here what we have is that we added this additional adder, which basically takes the PC and immediate and gets the PC plus immediate here and gets the PC plus 4 here, and then decide whether the next PC should be PC plus 4 or whether it has to be PC plus immediate. And that's how we implement the jumping or the branching for us. Okay? So this is the whole picture of our data path. The last thing is what is the deal with this ALU up and this ALU control, which I'm going to describe in the next slide. So far, is there any questions?
So even though 0 isn't technically from the controller, it's still a control signal?
So the question is that given that 0 is not technically coming from the controllers, it's still a control signal. Yes, to make things kind of consistent, we show it with blue. It's a control signal. It's not coming from the controller. Yeah.
Can you explain again? So what happens with the write data? Like what does that? Because I see something coming into the register, but I don't understand how it affects the output.
You don't understand what?
How it affects any output.
For registers.
Yeah.
So in order to understand that, let's look at, for example, something like SOB, right? So SOB has RD, RS1, and RS2, right? And what the SOB says is that do the SOB operation in these two inputs and save the results into this output, right? So if you follow that, you will see that basically this is the results of RS1 minus RS2 here. It will bypass the memory, and then it will also goes here. And here still we have RS1 minus RS2 here, right? And if you follow this, you will see that this is the write data to our register file. You will also see that the write register, which is the number for RD, is coming from this instruction here. If you remember on that table, we had RD at 7 to 11, for example, X5, X6, whatever, right? So this one says, for example, this is X5. This says this is the results that needs to be written to X5. So for example, this is X4 minus X3 or whatever these two RS1 and RS2 is. And this control register here tells that, yes, indeed, write to this register. Because there are lots of other instructions that doesn't have RD or doesn't need to update your register file. Not all the instructions update your register file, right? So for example, you have a store word, which basically updates your memory. So if you, for all the instructions, you say, oh, there is an RD and update RD, you're going to basically make a mistake and have an incorrect result, right? So this is basically kind of like, the write register is telling you when to write to your register. And the results, by the way, is not always RS1 and RS2. It could be RS1 and immediate, right? So we could very easily do RS1 and immediate. Or we could even do load word if you want to.
If those instruction lines that are going into the registers block are always going to be RS1, RS2, and RD, why do we have to include them every time?
Because these are the numbers. So the question is that if everything that goes into register file is RS1, RS2, and RD, why are we including them in our register file wires? The question is we have 32 different registers, and we don't know which one we want to write to, right? So these values is telling you which register are we reading. For example, are we reading X0 or X1 or X2 or X3 and so on for RS1. Same story for RX2. And same story for RD. Because, again, if you remember the instructions we had, we can have something like X5, X1, and X0. The same instruction could be add X6, X1, and X0. So this value 6 is basically this value. So this is 6, okay? And this is, for example, 1, and this is 0. Okay, so it's basically telling the register file out of these 32 options that you have, this is the one that I want to write. I don't want to write to all of them. I just want to write or read from this specific one.
So RS1 can have multiple addresses. It's not just one register.
So the question is, RS1 can have multiple addresses. For every single instruction is only one value, but for different instructions can have different values, right? So you can technically read from any of those 32, and you can write to any of those 32. Of course, x0 is always 0. So if you write to x0, nothing happens. But you still can technically write to x0. But it's just inside the register file is wired such that nothing happens to x0. Any other questions? Okay. So let's also describe this ALU control as the last part, and then I'll give you a few minutes to break. Okay? Okay, so what's the deal with this ALU control? Remember, we had R-type and I-type and S-types and all those things, types of instructions. For most of them, you just have one type of activity. We have either load or store and so on. For R-type and R-type, specifically for R-type, we have many different options. We have add and sub and XOR and so on and so forth. One option is, so first of all, the trick to use in order to distinguish these from each other was using func3 and func7, right? Some of them use both of them, some of them only use one of them. So the trick that we use, so one thing that we can do is, as one of you suggested, is that to the controller we maybe also wire func3 and func7. And kind of like, then in that case, we just connect this to our ALU and tell what the ALU to do, right? So that's one thing we can do. The problem with this is that our controller then is not symmetric for different operations. For some operation, it takes more time to decode things, because for R-type instruction, we first need to understand this is an R-type. Then we need to jump to another state, which is the func3. Then jumps to another state for func7. So worst case scenario, we need to jump 3 times. Versus for the store word, we only need to jump 1 time because we know it's to store and that's it, right? And designing an FSM this way is not great because, as you will see later, we want to make things as equal as possible so that the timing for different instructions are not different, okay? So what we do instead is that we decode R-type instruction in 2 steps. The first step is we creating this thing called ALU operation. So we basically, the ALU op just tell you whether this is an R-type or I-type or S-type and so on. Then we have this additional logic which called ALU control that gets this ALU op and then make a decision that whether this is an R-type and I-type. This will help us that our controller stays the same for all instructions, but if we need additional work, we just implement it in some other place in our system, okay? So let's actually see how we do it. Okay, so I'm not going to show it to you now because apparently I'm showing some other things first. But once we get to this part, I'm going to describe that how do we first create the R-type and I-type and so on here. And in here, I'm going to show you how we distinguish between, for example, add and subtract and so on. Before that, let me actually describe the rest of the controller design and then get to that point afterwards, okay? Let's have a quick break, and then I'm going to talk about these control signals one by one.
The shift left, like not contained inside the immediate generation?
Here?
Yeah, like
We can do that. It's just, again, the shift left, because shift left is just wiring. So in reality, this is, so if you have 0, 1, 2, 3, what all it does is connect this to here. So this would be the new 0, this would be new 1. So it's just a shift, it's just a wiring. So it's not really a logic, it's just a wiring. And that's why we're doing this system.
I might have the exact same question as him about the shift left by 1.
Yeah, so as I said, the shift left is basically nothing but just a wiring. So this is our immediate, right?
Yeah.
So this is 0 bit, 1 bit, 2nd bit, 3rd bit, and so on. And this is our shifted version. So all we need to do is this. And this is our new 0, this is our new 1, this is our 2. And then we just need to sign extend the last bit, and that's it.
So what's the reason the wires have to shift after? So like, I guess my question is, so you're rewiring it basically, right? Ignoring the 0 bits.
Yeah.
What's the reason for that?
So the reason that we are shifting things to the left was branch equal always needs to jump to +4 or +2. There is no reason that we want to jump to odd instructions, right? Because our instructions are 4 bytes or 2 bytes. If you use the 16 version, it's 2 bytes. If you use the 32 version, it's 4 bytes. If you use the 64 version, it's actually 8 bytes. So we never do the odd version. So the first bit is you can always ignore. And the nice thing about ignoring the first bit is that now you have this additional bit on the left side, which means that you can have bigger immediates, right? So I'm basically telling you that you had 12 bits and now you have 13 bits. So you have actually stored more things to it.
Got it. So this is just a way to ensure that you don't have odd addressing.
Yeah. You don't need odd indexings, odd addressing. So maybe you can use it this way to actually jump to higher locations in your memory, right? Because if I'm telling you that I have 2 to the power of 12 bits to jump, at most I can do PC plus that address. But if I tell you that I have 2 to the 13 option, like in our immediate, it means that I can jump to higher addresses, right? So I can cover bigger range in my memory.
I see. Okay,
Right?
that makes sense.
Yeah.
Thank you.
Yeah.
The same problem I want to ask.
Okay.
I don't have a problem about the homework. So
Mhm.
for the fourth question, I didn't use any condition of you provide.
You didn't use any condition?
Yeah, okay, because I can just calculate a humming rate.
Sure.
Is that
I mean, if you don't need a condition, sure, why not?
yeah,
yeah.
just make sure is that the correct way, like.
It should be. I don't know. If your logic makes sense. So usually, what you need to do is write it in C code and debug it and make sure that it works. If it works, it's just changing it to a symbol.
Okay, so do like if I submit homework, do you will run it as a assembly interpreter?
No, we don't. It's just your homework would be just for completion. It will be graded based on completion.
Thank you.
Hi, I just had a quick question on how like the branch and jump instructions work.
Uh-huh.
Like when we have the label, I can see how that works. But then when we're writing the actual assembly code, are we having instead of the label, we can't use the label here. Are we putting in the actual address or calculating the offset?
The offset to that.
Alright, so like if I'm trying to jump like back here, I would do like negative, say like 16.
Yeah, whatever that difference is. Yeah.
Okay, so like does the label just represent the offset in this case? Like whenever we write that? Okay, thank you.
Hey, how you doing?
Good, how are you?
So, just wondering, I have a question about the ALU with the ALU result output and the zero output. So why, again, is the ALU result connected to the address input in data memory?
Because if you look at your load word instruction and store word instruction, you will see that the address for that is equal to RS1 plus immediate.
Okay.
So in order to create RS1 plus immediate, this will be your RS1, this will be your immediate, and the operation would be add, and here you get your RS1 plus immediate.
Okay, I see. So it's specifically used for store word, and in the case of other operations, we would avoid the data.
Yes.
Okay.
So we are reusing this part for our address generation. We could have, as I said, we could have had another adder here just for memory, and then in that case we didn't need that. We could have just do this, right? But there's no reason to do that because our ALU is there and it's free. So let's actually reuse it.
I see. Okay. Okay. Sounds good. Thank you.
Yep. All right, guys, let's continue. So we want to talk about so we already know all these control registers. Read-write was for what? Anybody who remembers this? Read-write for writing into RD, right? So ALU source was for picking between the immediate and RS2. ALU operation was to decide which ALU operation we want to use, like whether we want to use add or subtract and so on and so forth. Memread and memwrite for load word and store word instructions. Mem to reg was deciding whether we want to use the data from memory or whether we want to use from the ALU, right? So this was kind of like, deciding whether we want to bypass the memory or not. And PC source was for branches, right? For branches and whether we have to take the branches or not, okay? So we are thinking about basically a state machine that's very simple. We are thinking about having 3 different states for our state machine, having like a fetch decode altogether, the execute then, and then writing back or storing data. So we usually call this FD or fetch decode. We call this execution, and we call this write back or storing the results back. You could easily have 5 or 4 or multiple different stages as you want, but our state machine is basically these 3 different states. Okay. So to again remind you of our instructions, these are our opcode, this is our RD, find 3, RS1, RS2, and if you go back to our data path, you see that's the reason that we, for example, do 7 to 11 here, and like 14 to 19 or whatever it was here, and so on and so forth, right? So question is, how do we create our FSM? Usually we have 2 options. We call it active low and active high. The active low and active high means that the default of all control signals would be some value. In our active high case, everything would be equal to 0. Unless we want to make it activated, then we assign 1 to it, okay? So typically that's what we usually do. So all control signals here, always they're equal to 0. And then, for example, if you want to write to our register, then we make this equal to 1. If you want to jump or if you want to read from the memory, we make it 1. But you can do the opposite as well. There's nothing prevents you to do active load. There are people who prefer it that way. In that case, everything is equal to 1, so the default is 1. It means that if it's 1, it means that it's not active, and if it's 0, it's active, okay? Basically what we do in this scenario, which I usually prefer, is using active high, which means that everything by default is equal to 0. Then we read the opcode and the current state, and based off that, we issue the signal, okay? So the 3 states that I told you, let's actually see what needs to be done in each of these states. The first state is what we call the fetching and decoding, or FD. In the fetching and decoding, so we are talking about the initial state, and then the first step should be our FD state, okay? So what is happening here? The thing that's happening here is that the controller needs to know what is the opcode. Is it an R type, I type, S type, and so on? And think about it as a big switch case, basically. When you want to implement this, you will say that if opcode is 0000000, for example, this is I type. If it's 01, it's R type, and so on and so forth. So you basically jump to these various states. So from here, you jump to all these, you jump to all these different, like 5 type of instructions, right? R, I, S, B, and so on and so forth. For now on, let's ignore func3 and func7. I'm going to get back to it when I describe the ALU control, okay? And as I said, you're going to actually implement this in your first project, which, by the way, we're probably going to release it at the end of the week, during weekend or something. So in order to design our controller, we have 2 approaches. One is that we say that, you know what, all the instructions, everything inside our system, including the fetching and decoding, execution, and writing back the results, all of them happens in one cycle. So basically, the positive edge of the clock comes in, the PC gets updated, and then afterwards, we're going to read the instruction, we're going to read the register file, we're going to execute it, we're going to save the results, and basically, we will do all these things until the next positive edge of the clock. Like, we update the PC and so on. And somewhere here, we are done with our instruction. And then we wait for the next positive edge of the clock to come in. And then we execute the next instruction. Okay? So everything, all these steps that require for one instruction happens in one cycle. And we call this a single cycle design. Okay? This is a single cycle processor design, the simplest way that we can design the system. And for now, we are assuming that we are only looking at single cycle systems, okay? Later on in the course, we're going to talk about pipelining and multi-cycle and those things. But for now, to make things simplified, let's assume that every single thing that needs to happen for one instruction happens in one cycle, okay? So in that case, then let's see actually what happens for every instruction. So we have R-type instruction, I-type, load word, store word, and branch equal. These are all the instructions. Remember, we're still just talking about that 10 instructions, okay? And these are all the control signals that we need to care about. And for now, let's ignore this part. I'm going to get back to it later. So let's see actually what happens for every single one of these. And let's actually work together in order to fill this table. And then in the next slide, I'm going to show you the fill table. So let's just start with R-type instructions, okay? What should be the value for read write? Anybody? Should it be 0 or 1? And remember, 0 means that it's not active. So for R-type, should be 0 or 1? 1, right? Why 1? Because we want to write to RD. So this R-type instruction involves writing to our RD, so it has to be 1. What about I-type? Anybody? So if you recall R-type was also like add-I, RD, RS1, and immediate. So we still need to save the results back into our register. So our read write should be also equal to 1. Let's do store word. Should the store word be 0 or 1? 0, right? Because we're not writing to our register. What about branch equal? Also 0, because we are still, doesn't do anything, it doesn't involve writing to our register. And finally, what about load word? 1, right? Because we are reading from memory and we want to write it to our register file, right? So 1, 1, 1, 0, 0. Anybody has any doubts why we're doing, why these numbers are here? Cool. So now let's talk about the ALU source. So remember, ALU source was this one that decides between RS2 and immediate. So what should we do for R-type? 0. Let me see the default. Yes. 0 means RS2. What about I-type? 1. What about load word? 1. What about store word? 1. What about branch equal? 0. Again, any question why we are doing this? Yeah. So the question is, what happens to all the other jump instructions? And remember, I'm just talking about that 10 instructions that I picked. Okay. Yeah, I'm just simplifying this because otherwise we had to have this big table. But if you're in doubt, we actually don't worry about that. We're going to add that in your homework. You will see it. Any other question? Okay. So branch, remember the branch was telling that whether this is a branch or not, and this is simple, right? So which one should be 1 and which one should be 0? So the last one is 1 and everything else is 0, right? Simple. And if this was active low, it was the other way around, right? So everything would be 1 and branch would be 0. What about mem read? Which one should be 1? Load word, not store. Remember, when we are reading from memory, load word should be 1 and not store word. So everything else has to be 0. For mem write, it's the other way around. And what about mem to reg? What about R type? Should be mem2reg should be equal to 0 or 1. So remember, 0 was coming from ALU, and 1 was coming from the memory. So 0 or 1 were R type. 0. I type. 0. Load word. 1. Store word. 0 or 1. 0. What about 1? No. What if we do 1? So for store word doesn't matter really, because we're not gonna read it from the register file anyway. And then what about branch? Again, doesn't matter. You can do either 0 or 1, because in any case you're not gonna read it from that. Okay? Only these. So if you look at the mem2reg, you will see that mem2reg is actually similar to reg write, right? So these three, so this one was 1, right? So for these three, we do care, but for these two, we don't care because we're not going to write to the register file anyway. So 0 or 1 doesn't matter, right? Does that make sense why it doesn't matter? So, and then since the default is 0, we usually just put 0 here. But if you had put 1, that doesn't matter.
When like a write reg is set high, will that not actually write to the register until the next clock cycle?
So the question is, when we are doing reg write equal to 1, wouldn't that write to the register in the next cycle? For now, just assume that everything happens in one cycle. Okay? So there is a trick that we use, which usually for our register, we use the lower edge in order to write things to it. There's a notion of what we call half cycle, which we're going to get to it in future. But for now, just assume that everything is written in one cycle. So there is no issue of clocking. Okay?
Why can't we just set mem2reg equal to memory?
Mem2reg equal. So the question is, why can't we just equal mem2reg to memory read? We can do that. I'm thinking about this. There is a scenario which we don't want. So for this, so first of all, remember this is like a simplified version. So for this case, yeah, it's the same thing. You basically only want mem2reg when you have a load word, right? In other words. Okay. So yeah, this is the table. Should be hopefully the same thing. If there's a typo, let me know. And now finally, let's talk about the ALU op. Okay, so ALU op is, as I told you, that by default we think that the ALU gets 4 bits, and that 4 bits is basically telling us what to do. And remember, we have these operations here, and we just simplify things with these operations, okay? So we have, if you look at the actual operations that we're going to do, for load and store, we need to do add, right? Because we need rs1 plus immediate. So we're going to use the ALU, but we're going to use it as an add. For branch instruction, we use it as a subtract because we want to do rs1 minus rs2. And for R type and I type, depends on whether we want to do add, subtract, and or. So 4 different operations. So in total, we need 4 different operations, right, for this specific scenario. So what we do is basically, for these 4 different operations, we just map these 4 different operations to 4 values. So for example, we call ALU op for add 0010, and same for here, and same for here. For subtract, we call it 010, and here 010, and then for AND we do 000, and for OR we do 001. Okay? Basically all we did so far is saying that, okay, we have 4 distinct operations in this specific example, and what I'm doing is that saying that, okay, the first operation is this bit, the second operation is this bit, and the third operation is this bit, and so on. Okay? And then you will see that why we are picking it this way in the next slide. But for now, let's assume that ALU, all it does, it takes a 4-bit value, and based off that, decide what to do. If it sees 0010, the ALU understands that this is an add instruction, so I have to do add. If it sees 010110, it means that it's a subtract, so it has to do subtract. Okay, so far so good. And so what we do next is that I told you that we don't distinguish between R-type and R-type instructions. So in other words, we need to kind of like do this in 2 steps. And the way we do it is basically this this kind of trick that we are using. So for this ALU operation, we think that this is a 2-bit value, and we are assigning it this way. So we are for load and store. So this would be W, by the way. We're going to do 0, 0. For branch equal, we're going to do 0, 1. And for R-type and I-type instructions, we're going to do 1, 0. Okay? And this is the way that we're going to interpret this. We're going to say that whenever I see ALU, and then afterwards, we're going to go to func3 and func7 here in this ALU control and add 2 more bits to it. So I'm going to add these bits to it. Okay? So here's what I'm going to do and why we're doing this. So on controller, I only know that whether this is R-type or I-type or load or store or branch. And if you look back at this table here, you will see that for load word, store word, and branch equal, we either do add or we either do subtract. And for R-type, we do other things. So here's the contract that we make for ourselves. We say that if the ALU op is 0, 0, it's always add. If ALU op is 0, 1, it's always subtract. And if ALU op is 1, 0, it means that it's R-type or R-type, and go and look at func3 and func7. Okay? So this trick, we only need to say basically what is these 2 bits. So if my decoder says this is R-type, I'm going to issue 1, 0. If it says I-type, I'm also going to issue 1, 0. If it's store, load, or if it's branch, depending on which one it is, whether I need add or I need subtract, I'm going to either issue 0, 0, which means add, or I'm going to issue 0, 1, which is subtract. Okay? So this ALU control here, then it's going to get 3 different values. It's going to get either 0, 0, 0, 1, or 1, 0. And this ALU control knows what to do with this. So if it sees 0, 0, it's going to just add 1, 0 to the left of it. If it sees 0, 1, it's going to add, again, 1, 0 to the left of it. And this, if you actually look at the table, this is add, and this is subtract. And then for this one, it actually now needs to go and read func3. And if it sees 1, 0, then it means that go and check the func3, and there are 4 different options for it. There is an add, there is a subtract, there is and there is or. Okay? So one more time. We are decoding this ALU operation in 2 steps. The reason that we are doing this is to make the controller simpler. Because R-types has all these different activities. We're showing 4 of them here, but in reality, it's actually much more. So what we need to do is that decoding this operations for ALU in 2 steps. In the first steps, we made this observation that for all the other non-R-type or I-type instruction, the only 2 things that we need is add and subtract. In that case, I'm going to say in ALU op, whenever I see things that are not R-type or R-type, I-type, I'm going to say 0, 0 for add and 0, 1 for subtract. Okay? This is the code that I'm going to use. And if I say 1, 0, it means that this is R-type and R-type, and I have no idea which one it is. So I'm going to just send that to the ALU control. Then the ALU control is going to get these 3 values, one of these 3, and it's going to do a very simple thing. If it sees 0, 0, it knows that this is add. It's just extended with 1, 0 on the right, and send it to the ALU, and this is our add. If it sees 0, 1, it means that this is subtract. And it's going to add again 1, 0 to the right and send it to the ALU operation, and that would be our subtract. If it sees 1, 0, it knows that now it has to work and figure it out. So it's going to go and check this func3 function, which actually, by the way, is we are sending it to ALU control here. And it's going to check this table here again and say, okay, what I got was 1, 0, so I need to dig a little bit deeper to see which one it is. If func3 is 0, 0, I will just do add, so 0, 0, 1, 0. If func3 is 0, 0, 0, it's again subtract. I need to go and check func7 and then figure out that, oh, this 1 bit is equal to 1, so I'm going to do 0, 1, 1, 0. If it's an add, luckily it's just 1, 1, 1, so I know this is AND, so I do 0, 0, 0. And if it's 1, 0, 1, it's an OR, and I do 0, 0, 0, 1. So you may ask why these are 4 bits, why we have only 4 different operations, because again, I'm not showing all the instructions in this case. There are other things like XOR, there are shift and all those things that I'm not showing it in this table for, but in reality there are also other entries in this table, and that's why we need more bits to represent them. Okay? So this basically, what we get here is that 4-bit that we talked about, but this is the way that we are generating that 4-bit. Okay? Any questions?
Yeah, so why do we need 10 bits of func7 and func3 just to generate only 4 bits of ALU?
So the question is, why are we using 7 bits of func3 and func7, why we only need, for example, 1 bit? The answer to that is 2 things. First is, these are reserved for additional activities if you want to, okay? And the second is, if you look back at the table here, we already have this space for R-type instructions. We have our opcode, RD, RS1, and RS2. So whether you use it or not, this is like a space available to you. So even if you say, oh, okay, I'm going to just treat this first 2 bits as my func7, but in the rest of these bits is anyway there, and it's going to be wasted anyway. So you just might as well try to do something with it. Does that make sense? So is that clear why we're doing this for ALU? Cool. So this is just simply coding. There is no, you could have so for example, someone might ask, why are we doing 0, 0 and why not something else? It's just the coding to make things simpler. Going back to minimizing the logic and all those things, if you actually draw the truth table for this, you will see that this actually minimized into less number of gates. Okay, so you're not showing the gate level of this, but just this is basically the thought process in order to get to that point. Okay, awesome. So this is your final picture of your data path. So now we understand everything in this picture. Does anybody have any question about any part of this?
So the controller decides the ALU output, is that stored inside the controller as well?
So the question is that the controller decides the ALU output, and does that stored inside the controller? And the answer is yes. Yeah. We need to kind of know the mapping, memorize the mapping inside the controller. Yeah. Again, how do we synthesize this is the question that hopefully you've learned in your digital logic design course. We're not going to go into that, the actual logic implementation of this. But just think about it that, yes, this becomes a logic and is actually implementable in hardware. Any other questions? So this is what you need to implement in your project. We're going to actually change it a little bit, not too much, but basically think about all of these as functions in your code, and basically this wires would be the inputs and outputs to your function. So from this function to that function, and then you need to kind of call them one by one. So it starts from left to right, and then for each cycle, you need to read one instruction and execute it and go to the next instruction and next instruction. Question? Say it again. Yes. the question is for add and subtract, we need to check both of them, and the answer is yes. You need to check both of them. Okay, so let's move on. So let's actually go through to some of the examples. So for example, for R-type instruction, let's see which of these units is actually being used. And as you can notice, some of them are grayed out, which means that they're going to be used. So R-type instruction starts with here, with PC, then goes into the instruction, controller will be used, register read 1, and RS2, and RD, and data. We don't need immediate generator, so this part is not going to be used. We're not going to use immediate, so this is actually where it's going to get connected from here to here. We're not going to use memory, so this part is also bypassed. We don't need this wire here, so this is also grayed out. We're going to select this one and then go back to here. And all these parts from the branch also doesn't be used, so this one goes up here, this one goes here, this one goes here. We're going to connect these two and get this like this, right? So these are the units that we're going to use, and as you can notice, there are some of the units in our data path that's not going to be used, which is totally fine, right? So we only use some of it, and some part won't be used. And the whole point of these multiplexer and this enabled like read write and read write and all those things is to make sure that this is actually indeed working correctly. So as you can notice, both of these signals are equal to 0, which means that nothing happens to our memory, and memory generally is completely ignored in this R-type instructions. Any question here? So moving on to our load word, the story is a little bit different. So we start from here, going here, here. We don't need RS2, so this line is grayed out. We need RD and data to RD. We do need immediate generator in this case. We don't need ALU operation, so we don't need func3 and func7. We connect from the immediate to our ALU source, from immediate to our ALU source. We're going to use add in our ALU source. And in this case, we're actually going to use the address for our memory. We're going to use this line, so this line is actually grayed out. And then we're going to write this back to our data, to our memory. For PC, same story. It goes this way, this way, this way, and coming back. All right? And this mem read is also equal to 1, right? So this line is also equal to 1. Okay? And then finally for store words, same story for all these parts here. We still need our immediate. So this part I haven't graded out, so this is like, exercise for you. But you can see that like which part's going to be used and which part is not going to be used. So we don't need this part, for example. We don't need this part. We do need our immediate. We don't need this part. We don't need this part. This will be connected like this. This will be connected like this. We need the address. We also need the write data. And this part and this part and the entire this part is not going to be read and used. This part also not going to be used, same as this part and this part. So we're going to just basically go here, 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 and here. Again, any question about load board?
Can you explain again why the ALU control unit, that oval, isn't used?
The question is why the ALU control unit is not used, because ALU operation, ALU op, so this is used, I would say this line is not used, okay? So, yeah. So we don't need func3 and func7 in other words, but we need ALU control. Okay. Yeah, so I take it back. We use it, but not using func3 and func7. Okay, 10% battery. And for ADI, what happens is we go here, here, we don't need this, we need this, we need this, we need all of these. In this case, we also need this. We don't need this. This has to connect it this way, this way. We don't need this. This has to go this way. And then we don't need this. This has to go this way. And then again, no, no, this way, no, and this, right? And then we always, the controller always used, right? So there's no question that we use controller or not. For every single instruction, we always use the controller, right? Cool. All right, so that's the story with our data path and controller. We fully implemented whatever you wanted. From now on, there are two things that we kind of like discuss. One is adding more things to our data path in order to support all these other instructions. And the rest of the story that we're going to tell in this class is how we move on from this very, very basic design to a state-of-the-art, modern, very high-performance system. Because this, as we will tell you very soon, is not great in terms of performance, unfortunately. So this is not being used these days in modern computers, but this was like the very, very first design of a computer with the data path and control. Okay? So again, very, very simple, but not very efficient. But I'm gonna, to understand why it's not efficient, I'll describe it in the next few slides. So in order to understand why it's not very efficient and it's not like so quick, is that remember we told you that basically we are assuming that the entire execution of one instruction happens in one clock cycle, right? So our clock cycle, if you ask how long this clock cycle should be, is basically the time it takes from here all the way to writing back the results here. So if this is, for example, 10 nanoseconds, our clock cycle should be at least 10 nanoseconds. If it's 100 nanoseconds, it has to be at least 100 nanoseconds. So the first question is that how do we calculate that? Going back to the figure that I showed you here for these different elements, you have to start computing this different path. And one thing to realize is that some of these paths are serialized. So for example, we start from reading from PC, so reading the PC, and if we don't read the PC, we cannot read the instruction. So the instruction has to wait for the PC to get updated, and then we can read the instruction. So in order to find the ultimate time, the read PC plus the time it takes for reading this instruction, so we usually call it insmam. Now we have these values, and now think about this as kind of like, flow of water. So basically, all these things happens at the same time, okay? So the delay for doing the immediate generator is in parallel with reading the registers, is in parallel with reading the control registers here. So at this point, whichever is faster, whichever is the slowest is the delay that it takes from getting from this point to this point. For example, if your immediate generator is so slow, is much slower than your register file, then what happens is your register file will be the critical path. If your immediate generator is the critical path, then this delay is basically defined by that time, right? So basically, what happens is we need to kind of like calculate all these delays, and then see, okay, at this point, this is the time it takes from. So this would be the max of reg file, immediate generator, and controller. Plus, then we go to this part. Then it would be your ALU, because ALU can only operate when it has all the data that it has. Then if we, for example, need to read the memory, it would be plus memory. If we need to bypass the memory, it's just the delay for this multiplexer and the delay for writing to our register file, reg write. So again, we're actually going to give you this in your homework with more details. But in order to understand how long does it take for one instruction, you have to see what is the path from starting from PC all the way to either writing to our memory or writing to our register or writing back to our PC. And some of them will be serialized, some of them are in parallel, depending on whether the data is available or not. And then you calculate all these things together, you create this big statement and add them together. And the maximum of that time would be the time it takes for one instruction to finish. Question?
So what did you write underneath read PC? What is inst mean?
Inst mem. It times it takes for the so the question is, what is this statement here? It time it takes for putting the address until the data is available. Because this is a memory, it takes some time. It's actually a quite long time. So basically what we need to do is we need to find the data flow, like, basically follow the data flow for every single instruction. For R type is different than I type, than the SW, than LW, and then the branch. And each one using different components. Some of them are grayed out and some of them are not. So you actually have to put these timings for all of them. And then basically your timing of your instruction would be the longest delay of among all these instructions. Because remember, we have all these different instructions and we want our clock cycles to be longer than the worst case scenario. And in fact, the worst case scenario is your memory load instruction, load word instruction. This is the path to it. And it also includes some muxes here as well, which I didn't write. And what does this mean is that every instruction has to be slowed down in order to accommodate the load instruction, right? So basically, since the load instruction is the slowest, your add instruction cannot be executed faster just because our clock cycle should be long enough to accommodate for load instruction, okay? And again, we can talk about this path for different instructions and so on. This actually would be one of the examples that, like one of the questions that we're going to give you in your homework to see what is the path for your register, for your R type instruction and load word to understand why load word is highest. But what I want to say is basically what happens is that the length of your clock, which basically determines how fast your computer can run instructions, because every instruction is one clock cycle, is determined by the maximum time of your R type, I type, LW, SW, and branch equal in this specific case. And unfortunately, this means that if one of them is really, really slow, everybody else has to wait as a result, right? So this is why single cycle is not the most efficient type of executing instruction, okay? Because in ideal scenario, you wanted to say, oh, if the R-type instructions are so fast, why don't we actually run them much more faster? Because, for example, R-type needs 10 nanoseconds to finish, and mem-type instruction needs 100 nanoseconds to finish. So we are basically sacrificing 90% of the time for the R-type. R-type will finish very, very fast, and it has to wait because it's just we have to also accommodate for load word instructions. Okay? So this is the problem with the single cycle instruction. There are various solutions for it, including the multi-cycle or having a variable clock for all of them and so on. And none of them are actually efficient. What is efficient, and we're going to talk about next lecture in Tuesday, is what's called a pipelining, in order to make things kind of independent from each other and then make things much, much more faster. And once we do that, you will see that this design becomes much, much more efficient, and that's what we are using these days in our modern systems as well, okay? But on the other hand, single cycle was very simple, very simple to understand, very simple to decode, very simple to implement, and all those things. And that's why for now, we're gonna start with single cycle as the first project, and later on, we're gonna add pipelining and all those things to it, okay? So now the question is, can we do better? And I'm gonna pause here, and we're going to talk about this is going to be the bridge to why we are designing things in pipelining and all those things. So this would be the story of our next week. And for your quiz, the story also stops here. So your first quiz would be everything that we have discussed so far. Okay? So don't forget, we're going to probably Okay. So I'm gonna post a homework, a short homework, basically kind of like, discussing things that we discussed here. And then hopefully we will post your project sometime during the weekend. And you probably have 2 or 3 weeks to finish your project. Okay? Any question? Final question? Yeah.